Okay, it's also has a bit of pressure to speak about atoms, especially in front of the founding fathers. So I'll try to just like put my vision on this, and this is based on joint work with Ludmil and Maxime. I'll try to expand some stuff on what Max just said, and as I was mentioning, this is really like mostly my own appropriation of the theory. I apologize if I took the build out of this, but that's the way that I could internalize this to myself. And actually, this is going to be most like birational geometry-driven talk. So we start like fixing some concepts and notation that we're going to use. To us here, all smooth projective varieties will be considered over the complex numbers, okay? And generically, G will denote some finite group, usually a cyclic group. We're going to consider G actions on our smooth projective varieties, which are like generically free and by regular automorphisms. And in this case, we always refer to X with this action as G variety for simplicity. And of course, in the realm of G-equivariant birational geometry, you're going to say that two G varieties shall be G-equivalently birational if they are birational by some G-equivalent birational map, okay, for considered actions. Some another terminology we have to fix is that of linear G actions, especially on projective space. They come from projectivization of linear actions. And since we always want to keep track of the smooth projective variety and the group, we made a node then by pairs. Maybe there is no sound on Zoom, I don't know. So we're going to consider this G variety X, and then we denote them by pairs, X and G. And we shall say that this pair is like non-G linearizable if we cannot find a linear action on projective space, making then X and the projective space G equivalently birational. Okay? So mostly what we're going to be interested in this talk is first, what atom theory has to do with questions in G-equivalent birational geometry, and especially what we can say about obstructions to non-linearizability of G actions on smooth projective varieties. So to start, it's very good also to recall some classical non-obstructions to these problems about non-linearizability of G actions. The first that I understand is like most classical one is about the existence of fixed points whenever you restrict to abelian subgroups. And there is this more, not sure what to say about it, but like some sort of more nice expression is that whenever you have your G variety X and you pick a fixed point, P, on that, then you collect the characters coming from the induced action on the tangent space at that fixed point, and you form this determinant. And this determinant actually is a G-equivalent birational invariant, meaning it up to sign plus and minus, it stays the same under G-equivalent blowups. And the third one that will come back later in this talk is about these modular symbols. It was firstly introduced by Kontsevich-Pestun-Tschinkel. We're going to add some more comments on that later. And again, the main focus of what we want to do today here is to try to explain how this theory of atoms can be first extended to the G-equivariant setting. That's not hard. Then look at the invariants that this yields. And then try to merge with some classical quantities, maybe coming from the geometry of fixed locus, and also with these modular symbols, to answer more questions in G-equivalent birational geometry. So I mean, it's gonna some sort of really being a talk about G-equivalent birational geometry in many ways. Okay? Oops. Sorry. All right, so let's start motivating with one example that I know people in G-equivariant birational geometry cared a lot of attention to it. That's the following. You consider this a smooth hypersurface of a multi-degree 1, 1, 1, 1. It sits in P4. It's rational over the complex numbers. And so the question that we want to answer is whether you can find some sort of group action that will make this action non-linearizable on this smooth projective variety that's rational over complex numbers. And the first result I would like to mention is this. So you see this multi-degree surface, hypersurface sitting in P1, cross P1, cross P1, cross P1. You consider some action induced from this ambient space that's just given by you swap the first and second and third and fourth factors on this P1, cross P1, cross P1, cross P1. Then you consider this restricted action, and the claim is that the X1111 with this Z2 action is non-linearizable, okay? And the way that you're going to approach this explicitly in this talk is by the means of a computation with G-equivariant atoms. I'm going to get there soon. But turns out that you can actually enhance this result by considering more generally this symmetric group, the group of permutations, S4, and then subgroups. And then under some conditions, you can actually show, classify what are the actions which will be non-linearizable in the setting, okay? But we are going to really detail this first case for Z2 actions, okay? So this shall be our motivating goal, all right? And in order to do that, I'll just now spend a bit more on Maxim's talk. And as I said, I'm going to try to put my own perspective on it. So it goes as follows. Essentially, the machinery that we have employed in this paper to approach G-equivariant birational geometry is no different from their approach to the non-rationality of a very general cubic fourfold. What we do, we put as input the Gromov-Witten data from a smooth projective variety. And then for these technical reasons that Max was just explaining, you have to consider this non-Archimedean field. Generically, you pick this Poisson series field. And what you get as output out of this bunch of data is actually a base and then a holomorphic vector bundle over this base. And this base actually, to myself, I always want to think of this as just some domain to your Gromov-Witten potential. That's it. I mean, so it's nothing but that. It's built out of the Cater cone and also the cohomology. And you consider this flat bundle over the base, cross this disk with this germ of analytic disk in this non-Archimedean field with this parameter U. You ask the existence of this connection in this F bundle, and it turns out that one of the covariant derivatives records this quantum multiplication and is also has this term given by this Euler vector field, which is some sort of part of this has this data coming from first Chern class, okay? So this is the basic A model, F bundle setup that I use to consider atom theory. I drew some picture here. So if you think, then you have your base space, Bx, built out of Gromov-Witten data. And that's the domain to your potential. Then you have the fibers. Here, when you set this formal parameter U equals to 0, you can identify this with the fibers of the tangent space at the point B of your base space. There is this distinguished vector field, Euler vector field. And turns out that for atom theory, as Maxime was explaining about with this motifs, in our very concrete case here that we're going to call Hodge atoms, what we do is a bit more geometrically clear in some sense. So I'm using this very non-standard notation on the right here, there on the group MT, this Mumford-Tate group. So you consider this category of pure polarizable Q-Hodge structures with considering Z2 grading, and this is equivalent to the category of representations of a certain group, that's this Mumford-Tate group. Okay, and this Mumford-Tate group, it will act on the base Bx of our F bundle, and will define a fixed locus there. That is this, I don't know, by this blue color subspace. And we what are really interested to consider these atoms are actually the restriction of this covariant derivative at the parameter u equals to 0 on this fixed locus. And what you're going to do is to search whether this operator now that acts on the fibers of your base, where is the locus that has like the maximal amount of distinct eigenvalues for the action of these operators. And out of this spectral data, you're going to define your local atoms to each of these smooth projective varieties. So then you give as input your smooth projective variety, then you build this A model F bundle, you look to the corresponding maximal decomposition by the action of this kappa vector field, and this will define the data. This spectral data associated to that is what you're going to call by local Hodge atom. Okay? And just like expanding a bit on what Max said. And the point is that then you want to collect all the possible local Hodge atoms for all possible isomorphism classes of smooth projective varieties, and then impose some relations. One of like the main important ones are that coming from blowups, because you want to actually get applications in birational geometry, and then you have this weak factorization, you need to understand the behavior of these collections under blowups and blowdowns. All right? So then the main point is that one of the consequences of Eritani's formula is that the atoms of the blowup, these local atoms of the blowup, they will decompose in terms of local atoms of the smooth projective variety, and also data from the center where you did the blowup. All right? So pretty much this is it. I mean, this is a small expansion on what Maxine said. And I come really like from differential, I mean, part of what he said. I really come from differential geometry background, and so the picture that I keep in mind is always like that. So you have your input, Gromov-Witten data, then you build this Bx, that is domain for your Gromov-Witten potential, then you look tangent spaces, but in a fixed locus. And there is this distinguished vector field, you have your operator acting on the tangent space, but something that's very important is that whenever you are like some sort of fixed locus, and that's differential geometry, you want to look to isotropy representation, right? And the isotropy representation that you're looking at are that coming from Mumford-Tate group. All right? And one of the main points of this theory to myself is that these decompositions into generalized eigenspaces and that coming from isotropy representation, they are compatible. And that's what makes the theory nice, to myself at least. All right, and then just to summarize a bit then, because with all this terminology, all these definitions, how do you actually like put your hands on examples that you can make computations and extract results from? The point is that from this huge set of actually hot atoms that you do by collecting all possible smooth projective varieties, you can see that they are realized as local atoms for certain smooth projective varieties. It comes from this equivalence relations that we are defining. And then looking to the generalized eigenspace for the action of the kappa operator, you can really, like, at least for the purpose of this talk, confuse these Hodge atoms in a smooth projective variety as these representations of Mumford-Tate group in a concrete smooth projective variety. And to these guys, you have to find a way to keep track of these invariants. So, like, okay, you have these decompositions given by these generalized eigenspaces. How do you keep track then in order to compare for different smooth projective varieties? So you have to assign certain invariants to that. And the way that you do this is actually by considering like just the dimensions of this generalized eigenspace, but also the Hodge polynomial associated to this component. Because remember, you are considering subspace in cohomology, and then it makes fully sense to build out this Hodge polynomial out of this quantity. And these are the invariants that usually you're going to keep track. Now, the picture that we really want to talk about today is about G-equivariant birational geometry. So you have to consider blow-ups along smooth invariant centers. And the first question that emerges, how you can make compatible this group action picture with this A model F bundle picture, and what is the relation between this and Mumford-Tate group. And more importantly is, from the purely heuristic point of view, if you are considering some smooth projective variety that's rational, why would put some sort of group action in terms of this decompositions of generalized eigenspace, why would that indeed lead to possible obstructions to nonlinear disability? And that's the kind of questions that you have to ask yourself about why an approach like that would work. And the point is that since you are considering smooth projective varieties with these regular actions by automorphisms, and the way that the base B is constructed, actually, the natural group action that, the group action that you are considering on your smooth projective variety, it will go to the base Bx. And then, instead of just looking to fixed points by this Mumford-Tate group, you can actually think about fixed locus by Mumford-Tate cross the group. And that's what lies on the base of this. And I mean, that's gonna say could be dangerous, especially in front of the creators, but that's the way that I like to think about this, because it took me some time to realize what does this really have to do with birational geometry. If you just look, at least for myself, that's the guy that doesn't come from algebraic geometry, why do you really get obstructions? The point is that whenever you have these two compatible decompositions by the representations and also by the generalized eigenspace, you can produce wrong Hodge diamonds, so that could not appear in varieties coming from blow-ups, just because you are packing them incorrectly, because you have to respect the composition comes from Gromov-Witten theory. And this is not different from what we are doing when you consider now these finite group actions. You restrict your deformation space here by considering this fixed locus by MT cross G, and then the chance that you get like even more wrong, let's say, representations stacked together are like higher, and that's the point. I mean, so atoms like these generalized eigenspaces, they can come together into like more complicated generalized eigenspace that could have the wrong properties and then lead to the sort of obstructions that we are looking at. All right, so that's what I'm gonna summarize. So just to before really going to this G-equivariant setting, just put a sort of a condensed version of Katzarkov, Kontsevich-Pestun-Tschinkel theorem. So this is the picture, I mean, at least I like to have in mind. So you pick your smooth projective variety, you choose this generic smooth point, and then you have this canonical decomposition of your cohomology. And it's completely fine for the purpose of this talk to think that this Hodge atoms will be these decompositions into these generalized eigenspaces. And the main property, because you know blow-up, you know Iritanis blow-up formula, is that two smooth projective varieties, they will be birational if the collections of these Mumford-Tate representations will coincide modulo those coming from subvarieties of dimension 2 and higher. All right, this gives us this non-rationality criterion. That's a d-dimensional variety contains an atom, meaning a representation of Mumford-Tate group that does not appear in varieties of dimension less or equal than d minus 2, then x is not rational. So this is the spirit. What we're going to promote now is actually, let's go to this G-equivariant setting and then obtain a non-linearizability criterion that's just similar to that. I mean, it's very natural extension. There's nothing that's really deep about it, all right? So the point, as I was saying, now you're going to move into this Bx that you just construct by actually the fixed locus by MT cross G. So this is smaller space sitting on this base. That's the domain of your potential. All right? And then in the same way, you just do this collection, but you have to do this in a compatible way to define your equivariant Hodge atoms. In a compatible way means that, so blow-ups are only permitted along smooth invariant centers by this group. And whenever you consider this projectivization of vector bundles, you have to consider G-equivariant projective vector bundles. And the invariant now that turns out is that, okay, let's not just look to these generalized eigenspaces, but let's look to the amount of Hodge classes that are actually invariant under the group action. So it's just certain refinement. We're going to see this more precisely in a very explicit example. But before going to this example, I think one of the main messages I would like to bring is there is this story that you actually go to. You collect all possible smooth projective varieties, you define your A model of bundles, then you look to these possible decompositions, and you impose these relations, then you can define these G-equivariant Hodge atoms coming from the possible local G atoms that you construct. And the nice thing, important to expect, because of non-rationality criterion, is that we want to know what are the possible atoms appearing in varieties in smaller dimensions, right? So this set here, let's go back a bit. This set is filtered by the dimensions where an atom can appear. So in the following sense, this set of equivariant Hodge atoms, G-equivariant Hodge atoms, it's naturally filtered by the dimensions of varieties where a given atom can appear. And then the criterion for non-linearizability, I'll promise I'll say correctly once until the end of this talk, is just that. So you pick your G variety of dimension D greater or equal than 2. If X contain a G atom, you can really think about this as just representation of MT cross G that does not appear in the atomic decomposition of a variety of a dimension less or equal than D minus 2, then this action is non-linearizable. All right? So now this X1111 is three-dimensional variety. So in order to understand these obstructions, it will be sufficient to fully understand what are the possible elements in this part of this filtered set until G-equivariant Hodge atoms of dimension up to 1. And then it turns out that you can classify this under the assumption, for simplicity, that this group that you're considering that's acting on your smooth projective variety, all subgroups of it acts in a linearizable way on P1. For instance, this is true for cyclic groups. Then the possible atoms in dimension up to 1 can arise only from points, meaning you consider orbits of points, and can come from curves that could be rational or with a positive genus, but the invariants that you can keep track of, they behave more or less nicely. So atoms that could come from points or rational curves, they have number of these invariant Hodge numbers in the subspace of your cohomology, which are 1, but if it comes from curve with genus greater or equal than 1, then you can have 2. So now we're going to see an example, and I hope these invariants are going to be clearer, and then I expect to convince you the way that you can actually put your hands on this and do computations based on these simply numerical invariants. So the example that we're actually doing is that we started with in the beginning, this motivating example. So you have this multi-degree hypersurface with this Z2 action. It's induced from the ambient. So then you decompose here on the right the Hodge diamond of your multi-degree hypersurface. And then I just split in red the corresponding classes appearing in this Hodge diamond, which are invariant under the group action. Okay? So if you look, this number rho here appearing would be like the summation. So 1 plus 4 plus 4 plus 1, so you have 10. But actually, if you only consider the contributions appearing in your Hodge diamond which are invariant under the group, you have only 6. So you see, I mean, that's the first sign that indeed there is a serious chance that you can get obstruction to linearizability for the action. And that's the example we shall approach. So now what you have to do is to look at what is the corresponding atomic decomposition, G-equivalent atomic decomposition, and try to see how this numerology will fit together, meaning the quantities for appearing for atoms and the quantities that are invariant related to atom. Namely, first, what is the atomic content of X? Now, I'm just denoting the multi-degree by X for simplicity. So you can compute, for instance, and you get 3 eigenvalues. Up to scaling, these are like 16, 4, and 0. And the corresponding invariants appearing to them, that's this rho and rho G and PT. So like this number of Hodge classes, number of invariant Hodge classes, and Hodge polynomial. If you look to this generalized eigenspace, so this, let's call this Hodge atom, G-equivalent Hodge atom associated to 16, you have only one Hodge class and only one invariant Hodge class, and the Hodge polynomial is this constant, Hodge polynomial 1. Now you do this for the second Hodge atom with parameterized by the eigenvalue 4. I mean, these are computations. You can compute this. I mean, I'm just collecting the information out of this. So you have then for the eigenvalue 4, you can check by just direct computation that it will have like 4 Hodge classes, but 2 invariant Hodge classes. And then there is this eigenvalue at 0, and it has 5 Hodge classes, 3 invariant Hodge classes, and a complicated Hodge polynomial. I mean, it's not constant. Okay? Now, what you do? Atoms allowed in dimension up to 1 here could be atoms for points, 2 points, or curve with positive genus. I just wrote like elliptic curve. But if you look on the cohomology of your guy, you notice that you have these transcendental guys, so it has to have an atom coming from elliptic curve, okay, out of your quantity. It means then that from this atomic content of X, if you subtract the contribution in the atom at 0 from the elliptic curve, so this 5, 3, you see as remaining parameters for your atoms 3 and 1. And in order to the action to be non-linearizable, this 3 and 1 should actually come from should come from atoms from points or 2 points. I mean, that's the point. And then the numbers that you would have, you would be able to write 3 and 1, these possible quantities, in terms of the quantities of atoms coming from up to dimension 1. But this is not possible, because you cannot write 3 and 1 in terms of 1, 1, and 2, 1. So this is just that, the way that you use your non-rationality criterion. You compute the eigenvalues, you attribute the numbers, then you look, okay, so what kind of atoms do I have here? Do I have atoms that doesn't come from varieties of dimension up to 1? And the way that you do this is generically you have like some sort of problematic atom, so this atom at 0, and the numerology will tell you that no, it's not possible that the remaining atoms have to get rid of the contribution from elliptic curve can be written in terms of contributions from points or 2 points. So that's the sort of computation. One of the trickiest and hardest part to do this sort of computations are actually computing these eigenvalues, right? And I mean, you always have to conserve somehow the amount of difficulty, and in this case it comes from really computing the eigenvalues and the corresponding generalized eigenspace. But once this is done, like the main philosophy I would like to emphasize here is that whenever you actually manage to compute the atomic decomposition, to apply the invariants and then verify the criterion is much easier. So one of the main difficulties rely here. And maybe what I want to say has some sort of spoiler to the end is in this G-equivariant setting, we can actually get better results pending some stuff I'm going to get there. Other incursion to this other part of the talk. This result that we just obtained was purely using G-equivariant atoms. Now, the question that stands is, all right, if you know these G-equivariant atoms, can you actually combine these with some other classical techniques and results in the realm of G-equivariant birational geometry to get some sort of like better numerical invariants, that it possibly would lead to some circumventing of doing this full business of computing these eigenvalues and quantum multiplication and this kind of stuff. And one of the first attempts passed through merging with this theory of modular symbols by Kontsevich-Pestun-Tschinkel. This is much more geometric. And the idea is follows. So you pick now your group that's finite, you assume it's a billion, all right? Then you look to the corresponding decomposition of the fixed point set, like into irreducible varieties. So you have this decomposition. Now pick a point, any point in one of these components. You look to the corresponding induced action on the tangent space of the variety at that point on the component. You will collect the possible characters here, this A1 alpha to A1n. This decomposition doesn't depend on the point on the component, but only on the component. But you make this uple here, like this, an uple of characters. And you do this for each of the components and form this quantity beta x. Like formally, let's do this, okay? This is smooth projective variety with finite group action, regular automorphism. This is finite sum, no problem here. But then you want to see this in a sort of group that will provide the following fact. Whenever you look to the image of this beta inside of this group we will just define now, this quantity is actually invariant under equivariant blowups. So this quantity built out of the character data will be invariant under equivariant blowups and blowdowns. So this will actually be birational invariant. All right? And this is given by this relation. So they are chosen in a way that after looking to this beta, into the image of this group that are generated by possible characters under some relations, you actually give some birational invariant, G-equivariant birational invariant. This is it. These are just these modular symbols. So one thing that you may wonder, well, okay, so how do you guess this sort of relations? It's not difficult to see. What you do is as follows. So you look to the action, then you look to a smooth invariant center. It may or may not intersect your fixed point set, right? Then you have to account to the fact that, okay, suppose it intersects, then you do equivariant blowup, the action will go to the blowup, and it may contribute with new fixed point sets. This new fixed point set will have a new decomposition, you look to the corresponding characters, and you want to kill these new contributions in relation to the original ones. That's just the combinatorics that you do. And the question that we first asked ourselves is, all right, if we consider some sort of generated group by taking data from atom theory and geometry of fixed point set, can we actually get some more computable and refined invariants for G-equivariant birational geometry? And we'll answer this soon. But before answering this, let's answer the other question that is as follows. All right, how good can be an atomic invariant, like, or an atomic geometric invariant combined? How good can it be? In the sense that here in this Kontsevich-Pestun-Tschinkel story, it's only considered characters. But what if we actually try to do similar story, understanding equivariant blowups, but take into account also geometric quantities, not only characters, like degrees of normal bundles to fixed point set components, before going to atomic theory. And then we have a sort of invariant that I just wrote in this very simplified form because I don't want to put complicated expressions for the sake of sanity, but the point is you can actually get some smooth invariants doing certain summations over the components of your fixed point set, such that I can tell explicitly. So if you are in the surface case with Z2 action, so this invariant here, it changes whether you are like depending on the dimension of your variety, but also depending on the size of the group, because this invariant takes into account characters. So if you are in the surface case with Z2 action, the summation here is nothing but the difference between the Euler characteristic of the corresponding fixed point set component minus, for components, sorry, is the number of fixed points appearing in your fixed locus minus the degree of all the possible curves appearing in the fixed point set the component. So it's a surface, you look to the fixed point set component. It could be either points or curves. So you count the number of fixed points and then you subtract for the corresponding degrees of the normal bundle of the curve components. This is numerical birational invariant. In the case where you have a threefold, then you see that, okay, so in the fixed point set component, I can have only points, curves, or surface. Let's take into account possible contributions to these three types of stuff. And that's what is written here. So if you have a point, you count this point. If you have a curve, you look again to the normal bundle, compute the degree of the second exterior power, and then look to the genus of the curve, and then take into account 2 minus 2g plus the degree. And if it's a surface, again, you look to this normal bundle to the surface, you look to this intersection, and then you take this into account. These are the sort of invariants considering only geometric quantities out of your fixed point set. It's like they sound very nice invariants, but in our examples that we could do, they have constant values. The ones from projective space, like 4, 6, or 8. So, I mean, this is like in now decent examples that you can try, I mean, meaning if you don't know that if you start with rational variety, you consider group action, and then you try to look at this, you actually see that it's constant. So it says nothing. You cannot, we couldn't get a single result out of this purely geometrically refined invariance. One example that we're trying to track with, trying to attack is this. So you pick a polynomial, monic, with degree 3k, k greater or equal than 2, and then you consider this affine equation, x1, x2, x3 equals to this polynomial. Now you consider this, so this is like in affine space, it's pretty much rational, and you consider, and the cohomology consists of only algebraic cycles, you consider this Z reaction that cyclically permutes this x1, x2, x3 factor. So the fixed curve satisfies that equation. X to the cube equals to polynomial x4. And because of the choice of degree, you can show that this is a curve with a genus greater or equal than 2. Now you compactify and then like smooth it out in a decent way, so you get a smooth projective variety which fixed locus has this curve. And the point is that if you want to show that with this action, this compactification and smoothification of this variety is non-linearizable, then you are not able, because the value that you get is actually 6. And so it's the same that happens for projective space P3 with Z3 action. So you can actually not see difference. And that was very disappointing. But yet, it will work in a way to stress the power of the merge of the theory of atoms with these possible quantities. And so this is indeed the strong theorem. So I, again, stated like that because there are actually 3 theorems that I try to condensate in one. But so you pick your smooth projective threefold with a regular generically ZP action, P prime, okay? And then what we'll take into account is either like a genus quantity or a curve, like the isogeny type of a curve, like with positive genus. And you consider this invariant. So you look to the fixed point set, again for the action, and then you take into account, okay, first, the number of atoms appearing, then the number of curves with positive genus or with some certain fixed isogeny story, and the surface also appearing. So, for instance, let's work out one case. So, this numerical case here. So, suppose that you want your invariant to take into account actually genus. So, this invariant that you get, you count the polynomial appearing there in the variety X, whether it has contributions, whether it has atoms coming from curves with positive genus. Then you also count the components in your fixed point set, which are curves with that genus, and you count also, then minus 2 times this quantity of surfaces that are ruled and this direction ruling that has positive genus has has this fixed genus that you want. So let me say, then you count the number of atoms coming from curves with positive genus, actually genus greater or equal than 2, then minus the fixed curves appearing on your fixed point set component, and the ruled surface such that one of these directions is a curve with that genus G. So this is the numerical invariant. So let's go back in this example. So in this example, the fixed locus is this curve C that by the choice of the polynomial may have genus greater or equal than 2. So in this case, this variety here, after you compactify and resolve singularities in a nice way, it will be rational and the cohomology will have only algebraic cycles. So it means that in this expression here, the number of atoms related to curve with positive genus is 0. There is nothing, because the variety itself is rational and has no algebraic classes. Sorry, has only algebraic classes. So the contribution from atoms is 0. But there is what in the fixed point set? A curve with positive genus, depending on the choice of your polynomial. So this quantity here that you pick, n tau curves, is actually 1. And there is no fixed surface, so it's 0. So then you have minus 1 as quantity for this invariant. And I mean, it's not hard to see that for a projective space, it can never have a curve with positive genus, neither a ruled surface where one of the components of this ruling has positive genus. And so the invariant is strictly 0 for P3. So with this invariant, you can actually show the nonlinearizability of this action. All right. I mean, I was just redoing this example, so we can skip it. I mean, yeah. So that's what I said. I mean, so like minus 1 is the corresponding variant to this guy. Now this, whoops. To come to an end, I would like to mention this surprising rigid result between quotations, and I'll explain the quotations in a moment. But one of the problems with atom theory is that you should actually, you want to do stuff in every possible dimension, but you have to understand complicated atoms. So if you want to do applications in dimension 4, it's sufficient to understand all the possible atoms originating from surface. And you have minimal model programs, so you can actually classify the possible atoms coming from points, curves, and surface. But if you want to go to dimension 5, this is complicated because minimal model program is not done. But in this G-equivariant geometry atomic theory, you can actually get results for every dimension. And in a statement like that no atom appears in this statement. I mean, so you pick a smooth projective variety, the dimensional, and you define a polynomial. Like this is just the Hodge polynomial. So if for some element in the group, the coefficient of the corresponding Hodge polynomial for this fixed point set component is greater than the corresponding coefficient for the original variety, then it's non-linearized. Okay, but where are atoms in this statement, right? They're not. But the point is that you can only prove such a result if you do atom theory. I mean, the proof relies on knowing G-equivariant atoms. I'll say 2 sentences about this in a moment. And I'll also explain why this result in quotation. But I think one of the main important aspects of this inequality is, okay, so you don't have to really worry much about this complicated story coming from atoms, a model of bundles, computations of eigenvalues, quantum multiplication. You get a statement like that, but I don't think it's possible to prove it without atom theory, and I'll explain how you get there. But I mean, some less complementary example is just this x1, x2, x3 equals to polynomial that we just did, then you can do in all dimensions with this kind of result. I mean, just consider this Z3 action that swaps x1, x2, x3. I mean, so it's properly generalized and give a application of atom theory in all dimensions. But why is result in quotation, right? So the point is that this result is obtained by merging G-equivariant atom theory with the theory of Chen-Ruan or string cohomology. But it is left, it's missing to do analogous Ziritan's blow-up formula in this setting. And so that's why it's like a result. Let me try to explain it better. So whenever you have this G-equivariant action, you have this genetically free regular action on your variety. Okay, so let's not stick to G-equivariant birational maps, but let's actually go to the corresponding quotient stack. All right? Then in this quotient stack, you have this string or Chen-Ruan cohomology. That's the singular cohomology of the energy stack. All right? So in the case you have finite group acting on a smooth projective variety, it takes this simple, like this very simple form, as in terms of the underlying vector space. So you consider the cohomology of the fixed point set, and you take the invariant part by the centralizer CG for each choice of element in the corresponding conjugation class. It turns out that you can define Gromov-Witten invariance in this Rorke-Foltz setting, and you can regard this Chen-Ruan cohomology with the structure of a quantum cohomology also. And the idea is to refine the data from G-equivariant atoms with the data coming from Chen-Ruan cohomology. So the pending part is that, okay, so once you have this equivariant Chen-Ruan quantum, once you have this quantum Chen-Ruan cohomology, you can do the analogous A model F bundle, and it will be built out of the data of a Chen-Ruan cohomology on the quotient stack. And you can actually identify this fixed locus by the action of G inside of this A model. And the conjectures that are pending to verify is that whether you can actually extend Iritan's work to this setting when you go to the quotient stack. And that's the missing ingredient to actually call this results without quotation marks. But that's not, there's this, it's written on the paper what sort of conjectures you should approach to prove. But what is interesting to us is whenever you have your smooth projective variety, then you look to the corresponding A model F bundle. And then you have this untwisted sector, and then also in particular you have this fixed locus by the action BXG. So the point is that you have to the cohomology of the fixed point set by any element representing a conjugacy class in the group, a structure of a model over the algebra given by the quantum product here. And this structure is actually allow us to refine the invariants. So I like to call them like atomic numbers, like electronic distribution of the atoms. So you pick your G-equivariant atom, and you can define these refined Hodge polynomials that you can see as really like electronic distributions. So a priori you have your atom, then you have this other Hodge polynomial coming from look to this further decomposition of the fixed point set. So if you are, in the case G equals to 1, this is just your original atom. But then if you pick another group element, you have this sort of refinement, and then you get as many as Hodge polynomials as you have different conjugacy classes. And this like can provide a sort of list that, to myself, this resembles some sort of electronic distribution. And that result is actually this corollary that I say is more or less surprising, coming from the lemma that if you have an atom that comes from a variety up to dimension D, necessarily this electronic distribution is constrained by the coefficient in the Hodge polynomial of your atom. It's just like a corollary of this. And so you have to really go to this string quantum cohomology and do this sort of enhancement and no blow-up formula for return in this case to get this result. But once this is done, many applications can come, and that's all that I want to say. Thank you very much.